All right, everyone. We'll get started. Nice to meet all of you. I'm Sid. I'm a field engineer here at Materialize. I've been at Materialize for just over half a year now, and I'm based in New York City. And I'm here to talk to you about some of the biggest challenges and opportunities in AI today. Really, what we're going to talk about is how to give AI agents fresh and live context to data to make confident decisions. Because today, AI strategies don't just depend on AI models, but access to data. And by the end of this webinar, I hope you'll get a clear picture of how we can design our data architecture so that agents can see accurately, make confident decisions in an easy to use and cost effective manner. And Kranti, just to answer your question, yes, I will. We will send out a recording after this webinar is complete to all of the attendees. Let me make sure the slides move. Awesome. So fundamentally, agents act in loops. It goes. Agents move in these three-step processes where they first observe something in the world, then they think about an action to take, and then act upon the world. And in this loop of observing, acting, and thinking, the agent moves closer and closer to its goal that it wants to achieve, and finishes its its behavior decision making. But the real challenge here is, I think the challenge that a lot of people think about is how agents can think more accurately or using the correct model for the AI agents. But in this day and age, in the past year, we've seen so many improvements, and there's so many different models to choose from open source ones to closed ones, that this part of the loop process is commoditized. And really, what we're seeing as the differentiator for an agent workflow that's successful versus one that isn't is how well can it perceive the changes that it's making, or view the world accurately in order to make the correct decisions. And we see that that is the differentiator for its actions. So in other words, thinking is easy, but perception is hard. Now, for this webinar, I'm going to use this example of a same-day delivery service company, Freshmart. You can think of DoorDash or Amazon Go, or Costco's delivery service, for example, any like grocery store delivery service. And they want to deploy a seemingly easy app to use agents to build out a smart shopping cart. You'll give a recipe, and the agents will go through its product catalog and decide what items to get based off of your preferences and what's available. And while this seemingly seems like a easy problem to solve or an easy product to build out, this actually touches on quite a few different data services that the company may have. It needs to pull different tables from its product catalog. It needs to see what items are currently being reserved by customers. And ultimately, it needs to apply business logic to know whether or not to add an item to the cart. And these can be very complex queries. So for every single item, recipe, or customer, the agent needs to make a complex query representing its business logic. And all this data typically sits inside transactional database systems like Postgres or MySQL, for example. These complex queries aren't really designed to be run on these databases, especially at the scale required to make this service work for all of the customers. And looking at the token and compute costs, you can really see those scale up as different customers add in their recipes, multiple. You see like a fan out pattern where one recipe might result in multiple different queries to find substitutes for items or look into the catalog, find multiple recipes. This can quickly get out of hand. And so while the data might be fresh inside the OLTP systems about what's in store, what's in stock, what substitutions you can make, it's a challenge to make sure that the result comes back fast as well because the queries are slow. Another way to think about this problem is using a data warehouse for this situation. Data warehouses are great at running those complex queries that represent your business logic, but the problem then moves from running a quick query to getting that data, that fresh data, into your data warehouse. Because each time someone, for example, purchases an item and we want to reflect that change in our inventory tables, that data needs to first flow into our transactional systems for our inventory tables, but then also go through a pipeline to go through our data warehouse. And what we can quickly realize is that we want to optimize for the time to confident action. And that really is how long does it take an agent to take an action and then see the result of that action to take the next step in that loop. If, for example, an agent sees a recipe for a smoothie that has peanut butter and someone is allergic to peanuts, it then maybe picks up and reserves an item for reserves an almond butter item, but simultaneously another agent needs to know that one more almond butter item or perhaps the last item was reserved such that it can take confident action. Else, no real user is getting a a great experience using the smart shopping cart otherwise. So we want to talk a little bit more about how an agent can take confident action by looking at something called reaction time. Now, I want to also do a quick aside here where there's been a lot of work and a lot of talk around vector databases, and vector databases are great at what they do, and we've spent a lot of time as an industry, a time and effort to create very performant and very effective vector databases. But fundamentally, vector databases store the rules for how the world works. This is, you can think of if X happens, then Y. Like what products should I be able to substitute, for example, or historical information about avocado pricing, for example. Vector databases don't store the fresh context that the agents need. For example, what your current inventory level is for certain items won't end up appearing in your vector database. So while vector databases are important and a fundamental part of AI agent workflows and AI data architecture in general, vector databases on their own are not sufficient to deliver on the promise of agentic workloads. There needs to be some system that can provide the fresh context for agents. One way to think about these fresh context, is through the idea of digital twins. Digital twins need to be maintained in operational space. They are typically canonical business objects that we would keep live and up to date. So for any business, we want to think of the nouns of those business. For example, for Freshmart, there might be a concept of a shipment or an order or a supplier, for example. And we want to make sure that the information regarding that noun always stays up to date. Digital twins fundamentally stay close to the operation, stay within the operational space. So they're anchored closely to the OLTP database, getting data frequently from those systems in order to have that fresh context that's in your database. And that's really what your AI agents will use, these digital twins, to semantically figure out what information it needs to take action. And at the same time, these digital twins can then also push out this data eventually into your data lakehouse or data warehouse for historical processing that isn't as time sensitive as AI agents as the AI agent use case can be. And the key really is that digital twins have to be fresh and correct, and they always need to be up to date in order for a lot of these AI agent use cases to really function. So that's exactly what Materialize is trying to solve, is be that system that can provide those live data products for businesses. Really what's great about Materialize is that you can define all of these views of your business that then make up a live data layer. And these views are also or they can also be known as live data products. And these data products are stable and they're written in code, most importantly. Because we write them in SQL and we only define them once, they're a part of our application. We put them into GitHub, we maintain them. As something changes about our data architecture, or we have, for example, new business objects, or something changes, for example, about our supplier, about our order, this is updated in our SQL and is kept stable. So it's a part of our application rather than being a short-lived piece of code or piece of SQL that we run over and over again. That's the fundamental difference between having a live data product over a simple or a data pipeline that we run through on a routine basis. So Materialize creates those live data layers for your business so that AI agents can then access that data fast and cheaply. But fundamentally, Materialize is changing how this work gets done. With a typical OLTP database, if you defined your live data products, you would write your SQL views that represent the nouns of your business, all of the information about different suppliers or customers, for example, and this data would be rerun when you need this work to happen. Materialize flips this pattern on its head and does the work when it comes up. Materialize keeps these views of your business up to date, which you can think of as your live data products. And then when something changes, that data is that incremental work is done immediately by Materialize, such that when an agent needs it or you need that data, it's available and ready to use. So the shift is from where the work is done to when it's done. Now let's go a little bit deeper into how Materialize works and how Freshmart can use this. So Freshmart will connect all of their different sources to Materialize that the AI agents would need. We can think of our inventory table, our customer preferences table, demand information, pricing information. This all ends up being stored in our persist layer, so it's stored durably. And really what Materialize wants you to focus on is not how much data you're bringing in. It's only the amount of data that we need to keep up to date, or that's actually important for your businesses to use. So you connect all of your different sources. Freshmart connects all of its different sources to Materialize. And then afterwards, we define our live data layer, our data products, using SQL. So this is our business objects, and this is the information that would be stored in our GitHub or wherever our application code lives. Now, just with this much done, this is the same as what a transactional database or Postgres allows you to do. It allows you to connect in all your get information from various places and then define views. If this is where Freshmart stopped, this isn't fundamentally any different than just using their transactional database. Every time the AI agent needs some of this data from the views, Materialize would do all of the work again and again every time the agent needs it, and we would find that this would be very, very slow and would break the product. really what's nice here is that we can index these tables. Indexing these tables allows Materialize to create data flows underlying these views. And with that, what Materialize will do is keep these up to date. As something changes, a new product shipment shows up, or someone reserves the last item, because we've indexed these different views, this data stays up to date and ready for the AI agents when they need it. Now, it isn't just that, or just this isn't enough, where if I gave all of this information, I'll go back a slide, all of these different views to our agents, the information is there, but the AI agents fundamentally don't understand the context of what these views or why these views are important. So what we can define using our MCP server is comments on these views. Else the AI agent needs to do extra loops to find semantic meaning, and may not end up with the correct answer. So giving these comments to the AI agents will then allow them to know exactly where to look in your data products. So looking at a whole at Materialize and how AI agents would use this ecosystem, the way it would work is something like this. You would connect, Freshmart would connect all of its different sources. That data would sit in the persist layer or in object storage. You would define different views that would be checked into your code and kept up to date in memory by indexes. The AI agents would then use the MCP server to semantically understand these different views and act upon those decisions, affecting the underlying source systems that Materialize reads from. Because Materialize is optimized for reaction time or updating these up-to-date views, these live data products as fast as possible, these agents can fundamentally move in faster, more effective, correct loops than with any other system. So looking at how this would be productionalized, we would give this as a tool to your agents. Your agents might have other tools, such as to retrieve from vector search. They would receive then a tool for Materialize to query Materialize for that live context when needed. And then as consumers of Freshmart use the smart shopping cart, our application would then spawn agents using these commands. And this example is using Strand's agent framework, but you could really use any of them, like LangChain or anything else. And this would allow every agent to have access to the tools we define here. So that's how it would look in production for customers. Now, one more important piece to talk about that really matters for these AI agent workflows is consistency. Materialize offers a few different serializability modes or isolation modes that gives Materialize an edge compared to other systems to build AI agents. Materialize doesn't just read information from these sources, just receives inserts or updates. It receives the full fidelity of information coming from its sources. What that means is it receives inserts, updates, and deletes from your transactional systems, and also preserves the transactional or preserves the transactions of the source system. To give an example, if, for example, 3 different transactions happen at once, Materialize would commit all 3 of those transactions at the same time rather than have an inconsistent state. So what that means is that you'll never end up in a place where your data is out of order. If we imagine that, let's say that a customer purchases one item and 2 other tables need to be updated at the same time, that data is not in an inconsistent state when it reaches Materialize. It's not that we would have, for example, one table that's at time 3 with all of the transactions and other tables that only have partial consistency. And this really matters for AI agents who need to make confident and correct decisions. You wouldn't want the agent to look in one place and see that the last almond butter jar was taken, and in another place see that, oh, there is one almond butter jar remaining. You'd want your data to be in a consistent state. So Materialize moves from consistent time 1 to time 2 to time 3 state, which is important for these AI agent workflows when you have so many different concurrent processes happening at once. You wouldn't want this inconsistency. So because of Materialize's benefits in reaction time and consistency, Materialize has a competitive edge in providing these fresh context for AI agents, and is a fundamental part of any AI agent workflow to really deliver that promise of the outcomes with AI agents. And from here, I'm going to give, well, first, I'm going to stop for some questions just on the slides, and then I'll give a demo of this AI agent workflow MCP server in action. So let me stop sharing for a second and take a look at the questions. All right, I'll give a minute just for people to write any questions, else I'll move forward with the demo. Okay. All right. Let me share my screen. So here we have Freshmart again, and we're going to look a little bit more closely at the data products for Freshmart. This is one element of the live data layer, or one noun of the data, are the canonical business objects they're creating. And we can think of a data product as an inventory item. Freshmart is a grocery store, so they have different inventory items, and inventory items have a couple different properties, but we want to specifically look at price. Price for these inventory items changes over time based off of demand, based off of supply, based off of discounting, etc. There's a couple different pieces that goes into it. Now, this inventory data product is represented as a SQL query. This is just a complex query that does a couple joins, aggregates, in order to define its different elements. If we ran this complex query directly on our transactional system for each and every item, it's quite slow to run. Here I'm running one QPS, barely one QPS, and it's taking 5 to 6 seconds to run just for one item. So as something changes within my data product, like the demand changes or the discount, for example, changes, it takes 5 to 6 seconds for the price to change. And while that could be okay for a smart shopping cart or an online service with many customers, that might be unacceptable at the scale required. The natural thing to do at this point is to, like the slides, is add in a data warehouse. In the data warehouse, the query runs a lot faster, but we end up with this sawtooth pattern where getting the fresh data into the data warehouse becomes a challenge. And what happens is that you end up with a sawtooth pattern where it takes a while for the changes, for example, in promotions or inventory levels, to hit the data warehouse and go through that pipeline. So this isn't necessarily the solution we're looking for. Next, let me add in Materialize. Materialize sits, I'm going to change this to I'll change this one to the log scale. Materialize isn't quite as fast at running the query as a data warehouse is, with all these complex joins and aggregates. But we see that the reaction time, which is, we can think of the time to actually see what's changed in the real world in our data, is lower than both the Postgres and the data warehouse in this situation. Because Materialize only does the incremental amount of work, the query runs a lot quicker than it would on a Postgres or transactional database. And because it's connected directly to that transactional store, it gets the fresh data, which is what the data warehouse struggles with. And that's really why Materialize is a great fit for these AI agent workflows. Now, with this, I can show, if I toggle a promotion and I change the price, Materialize updates almost instantly in 1 second. Postgres is still waiting on that to run that query and change its price. And the data warehouse needs to wait for the data pipeline to run again in order to update its price. And this kind of encapsulates why AI agents would need fresh data or need to see changes quickly in order to make action. Now, let's take this a step further. We have this system built out, but let's see how an AI agent would use this. Let me connect to my terminal, share. But before I do that, I see Michael's question. Are we assuming that Materialize is serving this data? Yes, Materialize is serving this data through, you can run queries directly on Materialize, or you can sync that data. Either works, but for this example, we're assuming Materialize is being queried for this data, like the which I'll show in 1 minute, that the AI agent is directly querying Materialize versus directly querying Postgres versus directly querying the data warehouse. Let me show this. Okay. So here I have Claude code, and I've defined a tool for my AI agent. This tool is the tool to query Materialize, which is what I'd shown from the slides as a tool all AI agents would get for the smart shopping cart. Now, this AI agent has a few different options. It can get the data products, it can see the details or the metadata, and it can also query. Now, let's imagine that we have this AI workflow built out, and the smart shopping cart is in production. What would the AI agent actually do? The AI agent might do a command, or might look up what's the price for a red delicious apple during its workflow. Now, over here, we see that it's 89 cents. And let's see if it will first come back with that. It's taking a minute. Okay, it got the price. Now let's toggle the promotion and let's say check again. you see it picked up that the price changed because I added the promotion, and this really encapsulates what Materialize was built for. It was providing this fast reaction time, or showing updates, or having views that stay up to date in real time. This is fundamentally important to these agent loops and agent workloads that we're building out. Now I'm going to stop sharing. That's the end of my slides and demo. I'm happy to stay on for the rest of the session to take any questions, and I'll be looking for any more questions in the chat. Michael, did I answer your question, or did you have any follow-ups from what I shared? Gotcha. I think let's connect offline, and maybe we can work out a solution to what you're facing. Okay. If there's no other questions, I think I'm going to close out this webinar. I want to thank all of you for attending. I'm happy to answer any questions offline through email or on our community Slack, if you want to post there regarding this topic, and hope we can all connect. Thanks, everyone.